to start with a little story from the classical computing world. So in 1945, the University of Pennsylvania, together with some money from the US military, builds the Electronic and Numerical Integrator and Computer, or ENIAC for short, primarily at first for the purpose of computing ballistic missile trajectories, but more importantly, this was the first general-purpose classical computer, right? So this classical computer cost them about $10 million after you adjust for inflation in today's money. And what did $10 million get you? It got you a 30-ton machine that could perform about 100 floating-point operations per second. So addition, subtraction, multiplication, division. OK, so fast forward to today, and we all have in our hands, pockets, or purses, one of these smartphones that costs hundreds of US dollars, maybe 1,000 if you're really shelled out, and can perform 10 billion floating-point operations per second. So how did we get here? I hope everyone in the room knows the answer. There's a phenomenon called Moore's law, which is just the observation that classical computing power seems to double roughly every 2 years, right? So a common way to measure this is something like number of transistors that fit on a chip over time. So you see these numbers on the left get very big very fast. But there are many ways to measure this doubling of computing power. So you can also look at hardware space, hard drive space. So USB sticks came around maybe 15 years ago. The first ones fit maybe a few megabytes. Whereas now if you go on Amazon for 20 bucks, you can get one of these with hundreds of gigabytes, or even a terabyte if you pay a little bit extra. So what does this have to do with quantum computing? Well, first of all, one similarity is that if we can realize multiplicative gains and sustain them as they accumulate, so quantum sort of computing everywhere, ubiquitous, is inevitable. And second of all, there are many ways to measure this growth in quantum computing power. So as a very extreme example, consider a device with 100 low-quality qubits, or perhaps qubits that are poorly used. Trying to use these to solve some problem you're interested in is about as good as rolling dice to guess an answer, right? Whereas on the very far extreme, if you have 100 perfect qubits, now you can actually start performing simulations with real scientific value, like simulating and designing better quantum sensors in the same way that you can classically simulate and design better airplane wings, right? I should say if you scale this up to 10,000 perfect qubits, that's roughly where we expect to start seeing a quantum advantage in applications like derivative pricing. So what do we need to get here? Well, yes, we need more qubits. We need better fidelities. I like to remind people there's a lot of theory work to do before we get to useful quantum computing. So this is theory work in designing better error-correcting codes. This is theory work in designing computer architectures at scale. But we also need better software. So this is software that controls the qubits you're using. This is software that leverages techniques from physics to suppress the effect of errors in your device on your outcomes. And this is software that compiles instructions from the level of flip this qubit down to a language that hardware understands, like turn on this laser. So if I wanted to be more provocative with the title of this talk, I would have said something like SuperstaQ powers Moore's law for quantum computing through software. So how does it work? What's the basic idea? Well, the basic idea is to break layers of abstraction. So traditionally, software is organized into what's called the software stack, which consists of lots of rigid layers and well-defined interfaces between them. So why do we do this? There's a very good reason. Computing systems are very complex. And sorting them into this hierarchical stack gives you sort of breaks up to chunks that are well-defined, that you can optimize one at a time. And so entire careers or industries can work at just one layer of a software stack. Right? But the stack also introduces problems that are pertinent for quantum computing. The first of which is that you lose opportunities for optimization when your program, or maybe your whatever quantum, your program or your application doesn't know what hardware it's running on. Right? Maybe there are different algorithms to solve the same problem, and maybe a particular piece of hardware is better suited to one algorithm than another. And second of all, the quantum computing stack actually changes over time. So we're still figuring out how to do this, how to do it well. And it's highly likely that useful quantum computing applications will precede whatever final stack we end up with decades later. This was just as true for classical computing as it will be for quantum. So we all take it for granted that computers run on zeros and ones, but in fact, ENIAC, the first classical computer, used a decimal number system from 0 to 9, which had major implications for how it was used farther up the stack. What's the point? All this is to say that if we're interested in useful quantum computation in the near term, or however near that ends up being, engineering to the quantum software stack is premature. And this is where SuperstaQ comes into play. So SuperstaQ is a platform that sort of takes any application or algorithm that a user is interested in and tailors it to a specific piece of hardware. So here's a data sheet, if you will. SuperstaQ is a write once, target all platform, which means that a user comes with their application or their software. They write it once, they specify it, and then SuperstaQ lets you run it on any or all pieces of hardware that you would like. For application end users, SuperstaQ has an application-centric API, which is to say that you don't need to know much of anything about how a quantum computer works to start using it. So as an example, here's like a very short code snippet using SuperstaQ to solve a minimum volatility portfolio optimization problem. And you'll see nothing inherently quantum in what's going on here. And then at the very extreme opposite end, for research end user, for the quantum researchers, SuperstaQ is pulse optimized, which is just to say that if you want to get to the nitty-gritty of what you can do with a piece of hardware, SuperstaQ will let you do that. All right, so you don't have to take our word for it. We already have several happy paying customers that have purchased SuperstaQ license, thereby sort of voting with their dollar. And in every case where applicable, they have renewed this license. So they've come back to us happy with what they've seen. And in addition to these, we also have some national bank international customers that I'll leave it to the business media people to figure out when and how to announce that. And finally, I want to highlight again that SuperstaQ really is cross-platform. So the astute viewer might point out that our parent company Inflection is working on a cold atom quantum computer, so we indeed support cold atom computers. But through these customers, we're also supporting trapped ions, superconducting qubits, quantum annealers, any device that they would like. How am I doing? Cool. All right, so with all that said, that's sort of the high-level overview. That's the general pitch. What I want to do for the rest of this talk is actually show you by example a little bit how SuperstaQ realizes these gains for quantum performance through software. And one of the best examples for this is some work we did with the Advanced Quantum Testbed, which is an experimental superconducting device at Lawrence Berkeley National Lab. So the story begins here with an application, a clustering problem. So you have a bunch of data. You want to somehow organize that data meaningfully into separate partitions and clusters. And there's a quantum algorithm for doing this called the QAOA swap network. Right? Details of the algorithm aren't too important, but the part we will zoom in on is the building block for this algorithm called the fermionic swap gate. So for specialists and researchers in the audience, you can take this little circuit at the bottom as the definition of the fermionic swap gate. But for generally the important part here to know is that this gate takes a single parameter. It's an angle. We'll call it theta. And so this is just like how, with a single qubit, you might want to rotate it by some amount. And you might have an angle that you pick to rotate it by, 90 degrees, 180 degrees, whatever. Here again, this is a 2-qubit operation, and it depends on some angle that you choose at some point. All right, so these are the ingredients that we're working with in SuperstaQ. And what do we do with it? Well, first, we notice that if you actually think about how to run this gate on the advanced quantum testbed, it turns out that there's lots of ways to do it depending on the value of this angle. So what I'm showing here is a circle. Every point in the circle corresponds to one value of this angle. And different colors correspond to different ways to actually run this gate with that angle on the hardware. Great. So we figured out different ways to do it. One naive thing to do is just say, oh, cool. Well, then, give me a gate with a certain angle. Whatever angle it is, I'll pick the best decomposition by, say, the one that has least error. And that's indeed something that SuperstaQ will do. But we go one step farther, which is we use a trick called equivalent circuit averaging to get even better results. And the way equivalent circuit averaging works is, it's a little silly, actually. Instead of picking the best decomposition for any given angle, you just pick a decomposition at random, and then you rerun your calculation every time picking a different random decomposition. Right? So you have a bunch of runs of this algorithm. Each one is a circuit. You have a bunch of equivalent circuits. And then you average over the results. And sort of intuitively, the reason this helps is because it turns out this averaging helps suppress systematic errors in calculation. So this is where you're consistently, say, over-rotating, leaving the laser on for too long. Unintentionally, but systematic errors happen. So what we're looking at here, some results, is for different values of this angle on the horizontal axis. On the vertical axis, we have some measure of error from running this gate on the advanced quantum testbed hardware. In black, you have the error you get from just the traditional decomposition of this gate. In blue, you do better if you just always use whatever best decomposition is available for a given angle. And then in purple is the level of error with this equivalent circuit averaging technique. So altogether, we find that we get a 2x reduction in error from running this gate for this application. All right, so that was quite a journey. But the point, really to emphasize here is how we started all the way from applications at the top of the stack and went all the way down to what the hardware is doing. Cool. All right, and this work with the Advanced Quantum Testbed was published just this year in the Scientific Journal of Physical Review Research for the extra specialists that want to dive deeper. All right, so another example, some work I did with Rigetti just in the last few months. Rigetti also has superconducting devices. And they recently released sort of very low-level, it's called pulse-level control over what these devices can do. And so say you want to run a circuit like this. This actually turns out to be a little silly circuit to run. I probably want to start the top qubit at some different state, but that's all a little beside the point. I have a circuit I want to run on their device. And I have low-level pulse control over what the device is doing. What this pulse control does is it exposes that actually hidden in this circuit are sort of these invisible idle or wait gates, if you will. This is one, you essentially just tell a qubit, just wait, sit there until I need you for something. Now, it's silly to think about these. Again, this is sort of like an empty instruction. What's the point here? Turns out these wait gates or idle gates don't come for free. So you have a qubit sitting there. You started in some state, here represented by an arrow pointing to some point on the sphere. And if the qubit just sits there, it'll experience something called dephasing, where it might rotate in some unknown direction by an unknown amount. Right? So I'm showing two possibilities here in blue and yellow. So it might have rotated left or right. And you don't know which has happened. So this is obviously no good. You don't want your qubits going off, changing what they're doing, while you just want them to wait and stand by. So you can use a trick called dynamical decoupling. So you can inject into these wait times electromagnetic pulses, a sequence of them, tailored to what you're doing. And what each of these pulses does is it flips around the state of this qubit in such a way that if these blue and yellow arrows continue rotating the way they did before, they come back to where the qubit was initially. So this is rephasing after it has been dephased. So I have an animation here. Let's see if it works out. You have dephasing. The pulse flips it around. And as they continue to rotate, they come back to where they were initially. So this trick is called dynamical decoupling. And what we find is that this trick increases the lifetime of the qubit by roughly a factor of 2. And this is pretty much, this is almost the first thing that we tried. So there's very little optimization that actually went into this, and we immediately saw these gains. So what I have on this plot is for different amounts of time that we might have let the qubit wait. I initialize the qubit in some state. I wait for that amount of time, and then I look at the probability that it's still in the same state. So in blue is what it does on its own, and then in orange is this very primitive dynamical decoupling sequence. So you'll see that sort of the fidelity of the qubit over time decays, in this case actually 4 times slower with the dynamical decoupling. Right, and we put out a blog also that came out just last week with AWS on how to use this pulse control through Amazon's portal, Amazon Bracket, to suppress errors on quantum devices with dynamical decoupling. All right, so the last example I want to give has to do with actually cold atom platforms. So this was looking at, this is based on how the cold atom system built by Inflection works. So the idea for these cold atom platforms, the thing to know about them that's relevant for this, is that there's sort of separation if you want to do something with individual qubits. There are certain things you can do locally. You can just rotate one qubit at a time. So in this case, it's like if you go spin around the North Pole, right? But other things, if you want to say take the North Pole to the South Pole, if you want to rotate them in some different way, you can only rotate all qubits simultaneously. Now, that's a little bit of a weird thing, but it's perfectly valid. One of the quirks you get, though, is that some things you want to do in individual qubits. So if you want to just rotate one qubit from the North Pole down, you have to decompose this into a combination of both global and local rotations, which is fine, but it turns out that this global rotation is actually one of the bottlenecks for runtime with these devices. So this is one of the slowest things that happens on the computer. So you want to be very frugal with your use of these global operations. Now, the good news is that if you have multiple local gates you want to apply at the same time, you can recycle the same global operations. So now the cost of the runtime of the circuit has something to do with the number of these layers of single qubit gates. And what that means is that if you have a circuit like this, what you want to run instead is not organized this way. We want to shuffle things around a bit and sort of optimize the schedule of these single qubit gates so that you have one time at the beginning when you run these gates all together. You run your 2 qubit gates, then again, using just a few global pulses, you again get a bunch of local gates. For the case of this circuit, this was pretty easy to figure out how to do this by hand, just by looking at it and kind of seeing, like, oh, I should shuffle it around this way. In general, that's not necessarily an easy problem. So what we did at SuperstaQ is we invented an algorithm to solve this problem with sort of a graph-based method. So it starts with a circuit. It converts it into a certain graph. So this is actually the same. This circuit is represented by this graph. These gray circles correspond to the single qubit gates that you want to schedule sort of together whenever possible. And what the algorithm does is it takes this graph and produces a schedule for you. The great thing about this algorithm is that it's not only efficient, it's actually provably optimal. So we have a paper we're working on where we prove this mathematically for any skeptical parties, that you can't do better than this algorithm for scheduling these gates. And in fact, if we go out there and actually try this algorithm on a bunch of random circuits, we find that you get roughly a 2 times speed up over the best algorithm we could find off the shelf to solve a similar kind of problem. And so for that reason, we have both a patent and a paper pending about the algorithm. So stay tuned. All right, so what are the takeaways? What do I want you to walk away with? The first is that software is a key enabler for quantum computing going forward, one of the important dimensions along which we need to make progress. SuperstaQ is a specific software platform that provides sort of multiplicative gains, so 2x gains all over the place for quantum computing applications. It's a cross-platform product. So you specify your application or your program once, and then we do the hard work of figuring out how to run it on any hardware platform in a way that's tailored to that hardware platform. And we use patented methods that have brought us happy recurring customers. All right, so since I have a captive audience, I'll really quickly plug. We have some more people, if you're interested more in what Inflection and SuperstaQ and SuperstaQ are up to, we have our president of quantum innovation platforms talking tomorrow on the intersection of quantum and finance. We have a VP of quantum software, Pranav Gokhale, presenting a new algorithm called SuperCheck for quantum advantage for databases. This is more stuff that's going to be built into SuperstaQ in the future. And then at any point, you could stop by the Inflection booth where Peter Knoll, our quantum solutions manager, can give you more introductions and demonstrations of SuperstaQ if you're curious. Thank you.
Thank you, Michael. Any questions? We have about a minute or two for questions.
Hi, I'm just curious about how you think about this as being different from a compiler, or do you think about it as just being a compiler? Just because you talked about breaking the abstraction layers in the beginning, and some of it seems like it kind of fits into the idea of being a compiler.
This is a good point. So in this case, this algorithm presented actually can be sort of thought of as a piece of a compiler, right? But that's not necessarily true of everything we do. This is why I started sort of with the AQT example, where part of what we do here is we look closely at what are the ingredients that go into this application, what kind of algorithms are suitable, and what ingredients do they have, and what kind of tricks can we play with them, right, for the given piece of hardware that you have, right? So if you just think about compilers on their own in the abstract, in the paradigm of, say, a quantum software stack, they don't know what hardware they're running on. And that's the big thing that we're breaking.